Okay guys, so this is Unit 4, Video 3 on inclined planes, or we call them ramp problems. Hopefully this one will be a pretty short video, okay? So the focus today is to basically be able to draw a free body diagram for an object that's on a ramp or an inclined plane, and solve for force normal, force down, friction force, and F net for the inclined plane. Okay, an inclined plane or ramp is any surface that has an angle with respect to the horizontal, so basically it looks like this. The three forces that are always present on a ramp would be Fg, normal force, and something we call F down, which is a force that goes down the ramp. Okay. Most of the time, force of friction is the fourth force. Okay. We sometimes use an inclined plane to gain a mechanical advantage or to make something easier. Notice how it's easier to push a box up a ramp than it is to lift one straight up. So we'll talk more about this in class, this mechanical advantage. But essentially, we use ramps like when we're moving and stuff like that, right? Because it's easier to push something up a ramp than it is to just pick it up and lift it straight up to the height that we need it to be at, okay? A couple notes about the forces. F down is part of gravity and is always parallel to the surface. Okay, it will go parallel to the surface. Gravity is always perpendicular to the ground, so gravity always goes straight down, okay? Normal force is always perpendicular to the ramp or surface. Remember, normal in math means at 90 degrees, okay? And the friction is always parallel to the ramp and usually in the opposite direction of the normal, or sorry, the force down. So if we have an object on a ramp, our free body diagram looks something like this. We have force down the ramp, okay? We have the normal force perpendicular to the ramp. We have gravity pulling straight down, and then usually friction, which goes up the ramp. Okay, it's not a very neat. Okay. All right, finding normal force and F down. So we actually have two equations to add to our notes now, and the normal force equation is force of gravity times, let me think, cosine theta, okay, and the force down is the force of gravity sine theta, where theta is the angle of the ramp, and it would usually be right there, okay, it's the angle that the ramp is at, so that theta is that theta, and then force of gravity is just force of gravity, right? So most of the time we can find these pretty easily if we're given these two things. The units of both of those things would be newtons because they're both forces, okay? All right, let's go ahead and do a couple examples. All right, so first I want you to just take a minute to think about how the F down and the normal force would change with the angle of the ramp. So if you think about if the angle goes up, right, if the ramp starts to incline more, oops, sorry. So if this angle goes up, so this starts to incline more like this, right, then how does the F down change? And if you think about that, right, and you plug numbers into sine theta, you'll actually find that as the angle gets bigger, right, the F down increases, right? As the angle gets bigger, the F down increases. And you could find that if you plugged in like sine 50 is 0.76 and sine 80 is 0.98. So you can see that as this theta goes up, sine theta goes up, which means F down goes up. Now if you do it with cosine 50 is 0.64. Cosine 80 is 0.17. So cosine is actually the opposite. So as the angle goes up, cosine of the angle goes down and normal force goes down. And that should make sense, hopefully, because as this ramp inclines and inclines and inclines, if you were to get it vertical, the normal force would almost be non-existent, right? Because the box would just sort of like fall straight down with gravity. There would really be no need for it to push up against the ramp, right? So F down is directly proportional, meaning that if the angle goes up, F down goes up, and the normal force is inversely proportional, meaning that as the angle goes up, the normal force goes down, okay? All right, let's try this example here. Calculate the acceleration of a 25 kilogram object on a frictionless ramp, so frictionless with an angle of 65 degrees. Determine the final velocity of the object after 4 seconds if it started from rest. So let's do the first part. Let's figure out the acceleration. I would advise you to always draw your ramps the same direction. It doesn't really make a difference, but for me it's just more consistent so that I kind of get the same idea every time. So we've got F down, Fn, and Fg. There's no force of friction because it said it was frictionless. Okay, so it's not going to move in this direction. It's not going to move toward the ramp or away from the ramp, right? It's going to move down the ramp, if anything. So the F net that we want is equal to F down minus the forces up the ramp, which would be nothing because we don't have friction, right? So it'd basically just be minus 0. There's no friction. So F net's MA, and then we just have MA equals F down. Well, we have an equation for F down, so if we plug that in, so Fg is going to be mg, so 25 times 9.8 would be the Fg, and then we have sine 65. So I'm going to go ahead and plug that in. Make sure your calculator is in degrees. Okay, so I get 25a equals 0.906. No, that can't be right. Hold on one second. Oh, oops. That's the sine 65, but it's not multiplied. Sorry, so it's actually 222. So then if we divide by 25, we get A equals 8.88 meters per second squared. Okay. Now the second part says determine the final velocity of the object after 4 seconds if it started from rest. So now you have a list of variables. We go back all the way to our kinematics, and we can just use this equation. Sorry, that one. Plug in. So it's basically just 8.88 times 4. So VF equals 35.5 meters per second. Okay. Let's try one more. This one has friction, so it'll be a little bit different. Okay, so a 15 kilogram object is traveling at a constant speed. That's key. So F net equals 0. Okay, down a ramp and experiences 100 Newton frictional force. Okay, let's draw this. So we just learned a good amount here. So we know that the down force is here, friction is up here, and it's equal to 100 Fn and Fg. Okay. Now, if it's constant speed, that means F net is 0, right? Because A is 0, which means that if this is 100, then F down has to equal 100 also. Okay. That's key. They want us to calculate the angle and the coefficient of friction. So the angle I think we're going to get from the F down, right? This is equal to Fg sine theta. So if we know F down is 100, we know Fg is m times 9.8. So I'll take 100 and I'll divide it by 15 and I'll divide it by 9.8. So I get that 0.68 equals sine theta. And then I'll do an inverse sine of 0.68. And I'll get the angle to be 42.8 degrees. Okay. And then, so that's that part. And then if I want to know the coefficient of friction, well, friction is always equal to mu times the normal force. So if I'm trying to find mu, I need the normal force. So I know friction's 100. I don't know mu. The normal force, we have this equation, right? So we've got Fg cosine theta. And now we know both of these things. So we have 100 equals mu. Fg is 15 times 9.8. Sorry, can't fit this here. Cosine 42.8. Okay. So 15 times 9.8 times cosine 42.8. So this is 100 equals mu times 107.9. And then I'll take 100, divide it by that 107.9, and I get mu equals 0.93. And that's it. Okay, so you're using these two equations and you're using what you know about the free body diagram of a ramp to solve these types of problems. Okay, so we'll do more practice in class, but that's it for this lecture.